One of the main problems when you want to make two wing parts are the spars, of course, and the joiner. So here we can see the spar on the carbon, on the fairing, and you could see that I first opted for this version of joiner, and you have an internal wall into the joiner. That was my first consideration. So of course, one of the consideration was, could I 3D print this joiner? It's a very short joiner, 32 millimeters. But also the question was about the spar that we are watching the first version right now. Could I print in 3D carbon filament in this spar? So you can see that it's showing perfectly. And you have some room here for a rib. So we can see now the rib that is coming between the joiner and the spar. The basic design was about this joiner plus the two spars, including the detailed roll, as you can see on the video.
First of all, why it's not fully working? It's not stiff enough. We want to know what is the thickness here, and the thickness is less than 1 millimeters, and this is too narrow. I have to thicken the wall here. I need to remove this wall, this one, and I will use it to cut my Russell, and I will introduce the Russell between the two walls, and I will around the Russell put some carbon. Normally you would like to have 45 degree here and minus 45 degree here on the wall, and normally on the top and the bottom, the top especially carbon, directional carbon, and on the bottom normally you make a mix between Kevlar and carbon, because simply it's not a plane for aerobatics, so you don't need a lot of compression on this side. You need more to have really something that it is very tough on elongation. So the Kevlar is the best, 100%. Next step is to rebuild this, and I have another problem with the 3D print, and this is not a little problem. Look, normally the size here 13 millimeters and 10 millimeters. But the problem I have is the final product is 10.3 millimeters. Therefore, it is not capable to fit into the main joiner. That's a big problem, because of course you don't want to remove too much of the material because it will become very brittle. And there is another problem, so I will show you with this story of inaccuracy, because with carbon filament you need to use another of 1.6 millimeters. If not, if you are using a smaller one, you can get more detail and maybe more inaccuracy, but you will suffer from clocking. And when you are clocking, it's very difficult to remove this clock. So let me show you the second problem that I have. So normally the spar is calculated to let 0.6 millimeters between the top and the spar, and the same between the bottom, the intrado, and the spar. If I get an inaccuracy of 0.30 millimeters, it removes the margin that I have, because of course here I will have some carbon to put, and additionally I need to reinforce with unidirectional carbon, especially on the extrado. In this type of small plane, every unit really matters. You really need to be very accurate and to check your parts every time, because of course you don't want to put for the weight, for weight reason, of course, but also because if you put a lot of microballon on the top and bottom, it's not really effective about stiffness. Microballon is not really a good thing about stiffness. So I have fired the part, removing the central spar, and I have thickened the flanges. So we can see that we have like a box, so the wasser can fit inside. And I've tried to get some dimension that I need to make a minimal cut for the wasser. Okay, it is printing right now. I have simply modified the percentage in the wire and the x-axis, reducing of 2%, trying to take in account that the 3D printing is not really accurate, to reduce the size of the part. The weight should be around 5 grams and a half, which is quite heavy in my opinion, because I have to add the wasser and some carbon. So the total operation with the main joiner and the two spars should be around 18 grams, which is not so bad, but I think that doing this in full carbon, full composite, should save, in my opinion, few grams. I wanted to show you some parts that I did with filament carbon in 3D printing. This is the main spar that you have seen on Fusion 360. 32 millimeters with a hole inside. You can see here that there is no hole. The problem I had is, first of all, I told you that this is not really accurate. So I had to grind this, the spar. And when I inserted with some forces inside the joiner, what happened? The joiner broke here and started to open like this, which means that with little forces, my main joiner was gonna to break. So I cannot imagine during a flight, or if you land a little with little forces on the floor, you will break the joiner like nothing. So I was not happy with this solution. So this is the spar that you have seen on Fusion 260, and normally it works like this, like this. But look, this is the flanges of the spar that should be inserted into the wing, okay? And normally, this is the part that is entering in the main joiner. But now I will show you something. Look. It's very brittle. I can break it very easily with my hand, carbon filament. So I cannot work with this in such dimension, not at all. The conclusion of this trial with filament carbon 3D printing, and I have post-cured 100 degrees for 6 hours my parts. It's better. It's really better. You feel, I would say, more stiffness, but it's still brittle. That's part that I post-cured, and I will break it. Oh my gosh. I cannot use this. The only thing that I can use is this one. 1 millimeters, so I will improve the thickness to 2 millimeters, because yes, it's very useful. I will work with this one, but this is the only part that I will keep. If you compare, this is a joiner for F5G, and this is another one. It's a carbon Russell one. So I think it's around 10 grams, and you cannot beat this. Okay, in the future I will try carbon filament 3D print
this size maybe. I will make some try because of course this is very teeny proportion for filament carbon, and I think that you need more volume and to use some internal structure to reinforce it and to put more carbon on, especially on the central part, and it could work. Or you use a mixed technique, 3D printing with filament carbon, and you use some raw cell and some natural carbon. Okay, that could work, probably with bigger size. So here we are in front of the 3D printer. That's a Bamboo Lab. And the secret sauce to make certain filament carbon is this device. Purely and simply, that was really a game changer. When I started to dry my filament, so now we have 57 degree of humidity relative, and that is what matters really. You have to draw to something like 32, 35, and then it makes your pot really strong. And this is only because I used such a dryer that I was able to consider using some filament carbon to have real spar used into the wing directly. You have type of material, the time here. So the price of such box is around 75 bucks, and I absolutely recommend a dryer. And I like this one because it displays all the necessary information. And also things that I like it is that simply generally you put the roll here, and the roll is it's not logical because the filament is going in an onward direction to the 3D printer. That's really more natural to have the filament going really in the right direction and going into 3D head. So we will compare here the standard specification parameters for the 3D printer in the slicer. So Bamboo Lab is using his own slicer. It's a proprietary slicer. I want to show you on the right, you will find here the parameters that I have registered specifically for the spar for my A5 key, and we will compare to the left window with the standard specification for carbon filament. So we can see right now that I have a teeny layer, 0.18 millimeters. So I need to show you everything so you can have an idea, and so you can copy all of this into your. So that is about the quality. It's about also the precision. That has the resolution has dropped to 0.001 millimeters. We have a finest elephant foot compensation, and we have already seen this spot. About the strength, we have asked rect linear here, and we have asked 1 millimeter top shed thickness, and this is very important. And the bottom shell thickness is 1 millimeter. That's really the most important.
because here by default is 0 and 0.1. The second thing is I have asked to fill the inside part of the spar with the geared sparse infill pattern, and I have asked 40%. This is really important for the stiffness of the spar. For the rest, it's almost the same, except that this parameters is 1 mm rather than 0.8. I think that I have, now we are in the speed, and I have decreased a little bit speed, but not so much. In fact, the top surface I have lowered of let's say 20%. So I'm showing you the exact parameters that I have used. So for the bottom of the menu, it's exactly the same, just little less speed. Support, I tried to avoid support, so normally there are no support here. Normally nothing has changed compared to what is usually done. Let's see this one, the last one, last menu, and normally it should be the same. Yes. So it's mainly about the thickness here of the top shell and the bottom shell. It is the most important, and also about your flanges and the density of geared inside the pot. That is really the most important. So I will redo this one time more to let the French, because I have a public in French, so I will restart the application for them. So for the one who speak and French and English, they have another chance to get all the parameters. I have recorded specific parameters for the carbon filament spar for my F5 key. So we can see that we have different value here. I just want to show you again all this value. This one has really changed. The resolution has changed also. The compensation here have changed to timeless, and we have also these parameters. The most important was here, resistance. So I come back on the top. So we have some things like rectilinear, 1 mm for the top layer, 1 mm for the bottom, 40% of infill density, geared, and the rest is almost the same except this one that is now 1 mm. About the speed, it has changed a little bit, 35 to 30, 55 to 50, and this one has not changed, except here the top surface has changed from 150 to 120, and the rest is normally the same. Support we don't need, So we will go here to this one. And this one has not changed. I want to say really that this allowed with the drier having such parameters to really build a strong spar, and in the next sequence we will see how it sustains the forces in case of a lot of tension, and I will make some break test on this spar, and we will see this right now. So now we'll start a destructive test with this spar. So that is the filament carbon spar that had been 3D printed. And I will use this tube. So the tube is inserted in the spar like this. And here I know that I have 75 centimeters. And so that's half span of the wing. So I will insert this into the vise like this to conduct the destructive test. And I'm using just a balance, something very basic. And I will put this on 0. It's very primitive. And I will try to know what is the forces until it breaks. 400, 500, 600, 700, 800 grams, 900, 1 kilo, 1 kilo 100, 1 kilo 200, 1 kilo 300, 100 kilo 400, 100 kilo 1 kilo 500. The final version for the moment for the spars. So I did several destructive tests and to know. So the final version should be in filament carbon with the drier, with the new parameters that I put into the slicer. So I showed you all of this. The joiner, the old version was this one with the detailed hole, and the new version is a straight one, and this is this one. I will not keep the joiner in carbon filament because it will be never stiff enough, never. So in another video we will see the mold to build this joiner in epoxy carbon, so this traditional method for composite. The external accurate dimension are normally, of course, respected in a mold. The problem is more internally because your spar needs to fit accurately inside. And I think that I found out a tip to solve the problem of the internal accurate dimension. So I will tell you this in another video. In this other video, I will do probably some, and I will show you this, some mold for a composite, epoxy carbon, traditional composite spars. But this spars, you know, is quite special because it's twisted. You cannot make a mold in two parts. Simply, it's not possible because nothing is plain. Everything is twisted, almost every faces, because it follows the profiles. The spar is following the profile inside. So the spar is only like just a longitudinal cut of the wing. So I will show you a 4 parts mold, a mold in 4 parts for each spar, because you have a left one and a right one, that's not the same mold. So we will see this in another video. So if you have some experience with the 3D print and what you do with this, so drop some comments. we can have more change.